This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Hey everyone, welcome to today's discussion. We're diving into the Angular Damping Simulator, a web-based tool seemingly designed to visualize the effects of damping on angular motion. For those unfamiliar, imagine a pendulum. How does friction slow it down? This simulator likely shows that visually. What are the core concepts this simulator aims to illustrate?
The simulator demonstrates the impact of damping on oscillatory systems, specifically those exhibiting angular motion. It allows users to visualize how different levels of damping, no damping, light damping, critical damping, and heavy damping affect the amplitude and frequency of oscillations over time. It's a great way to understand a fundamental concept in physics and engineering.
So it's all about visualizing the relationship between damping and the angular displacement of, say, a rotating object. What kind of mathematical models might be underlying this visualization?
Yes, precisely. The underlying models are based on differential equations that describe damped harmonic motion. These equations incorporate factors like the mass of the rotating object, the spring constant, if applicable, and the damping coefficient, which determines the strength of the damping force. The simulator likely solves these equations numerically and plots the resulting angular displacement as a function of time.
That sounds pretty advanced. Could you explain the difference between the various damping types shown, no damping, light, critical, and heavy?
Sure, no damping means there's no frictional force to slow the oscillation. It continues indefinitely with constant amplitude. Light damping means the oscillations gradually decrease in amplitude over time. Critical damping represents the optimal damping level, where the system returns to equilibrium as quickly as possible without oscillating. Heavy damping means the system returns to equilibrium slowly without oscillating.
So critical damping is like the Goldilocks scenario, not too much, not too little damping. What are some real-world examples where understanding these damping types is crucial?
Exactly. Critical damping is ideal in many applications where you want a system to settle quickly and smoothly. Examples include shock absorbers in cars to minimize bouncing, the needle in a measuring instrument to quickly settle at the correct reading, and even the design of certain building structures to withstand earthquakes.
That's fascinating. The simulator shows a few example equations for angular position. What do these equations represent, and how do they relate to the different damping scenarios?
Those equations represent different mathematical models for angular motion. The simple ones, like 2 sin t, represent undamped oscillations. More complex equations could incorporate damping terms, allowing the simulator to model the different damping scenarios. The specific form of the equation depends on the system's parameters: mass, spring constant, damping coefficient.
So the equations are essentially the recipes for creating the different oscillation patterns we see in the simulation. Is the simulator interactive, allowing users to adjust parameters and see the results in real time?
Yes, that's a key feature of a good simulator. Users should be able to adjust parameters like mass, spring constant, and damping coefficient to explore how these changes affect the system's behavior. This interactive element is crucial for understanding the concepts intuitively.
That makes sense. What are some of the limitations of such a simulator? Can it perfectly model all real-world scenarios?
No simulator is perfect. Real-world systems often exhibit nonlinear behavior, which might not be fully captured by the simplified models used in the simulator. Also, external factors not included in the model, like air resistance, can influence the system's behavior. The simulator provides a simplified, idealized representation.
So it's a valuable tool for learning, but not a perfect replacement for real-world experimentation. What are some potential improvements or additions to this simulator?
Adding more complex models to account for nonlinear effects would be beneficial, including the ability to simulate different types of damping forces, e.g. viscous damping, Coulomb damping, would also enhance its educational value. Visualizing the energy changes in the system over time would be another great addition.
Those are all excellent suggestions. The header information shows it was compiled using EJS. What role does this technology play in the simulator's functionality?
EJS, embedded JavaScript, is a templating engine. It likely helps in dynamically generating the HTML content of the simulator's user interface based on user inputs and the simulation results. It allows for a more interactive and responsive experience.
So it's the behind-the-scenes engine that makes the simulator interactive and user-friendly. The header also mentions a Creative Commons attribution license. What does that mean for users of this simulator?
The Creative Commons attribution license means the simulator's code and resources can be freely used, shared, and modified, provided the original creator is properly credited. It promotes open access and collaboration within the educational community.
That's great for promoting open science and education. The header also shows a last modified date. Does this mean the simulator is actively maintained and updated?
The last modified date suggests the simulator's code was last updated on that date. Whether it's actively maintained depends on the author's ongoing involvement. However, the availability of the source code under a Creative Commons license makes it possible for others to contribute to its maintenance and improvement.
That's a good point. The fact that the source code is available makes it a valuable resource for learning and further development. What would you say is the overall value of this angular damping simulator as an educational tool?
It's a valuable tool for visualizing a complex physical phenomenon in a simple and intuitive way. The interactive nature allows users to experiment and develop a deeper understanding of the concepts of damping and oscillatory motion. Its open source nature further enhances its value by allowing for community contributions and improvements.
This has been a great discussion on the angular damping simulator. Thank you.